Hello, I'm Michael White. Today I'm going to be reading from the 7th grade science textbook. We're on Chapter 1, Lesson 3, Scientific Inquiry. My Planet Diary. The Law of Falling Objects. Misconception. Heavier objects fall faster than lighter ones. This assumption is not true. They actually fall at the same rate, or with the same acceleration. The misconception was introduced by a philosopher named Aristotle and accepted for more than 2,000 years. But in the late 1500s, Galileo Galilei discovered something different. All free-falling objects fall with the same acceleration. To prove this, Galileo performed a number of experiments. Galileo's experiments involved rolling balls with different masses down a ramp called an inclined plane and making careful measurements. What is scientific inquiry? Chirp, chirp, chirp. It's one of the hottest nights of summer, and your bedroom windows are wide open. On most nights, the quiet chirping of crickets gently lulls you to sleep, but not tonight. The noise from the crickets is almost deafening. Why do all the crickets in your neighborhood seem determined to keep you awake tonight? Your thinking and questioning is the start of a scientific inquiry process. Scientific inquiry refers to the diverse ways in which scientists study the natural world and propose explanations based on the evidence they gather. Some scientists run experiments in labs, but some cannot. For example, geologists use observations of rock layers to draw inferences about how Earth has changed over time. Posing questions. Scientific inquiry often begins with a question about an observation. Your observation about the frequent chirping may lead you to ask a question. Why are the crickets chirping so much tonight? Questions can come from your experiences, observations, and inferences. Curiosity plays a role too. Because others may have asked similar questions, you should do research to find out what information is already known about the topic before you go on with your investigation. Look at Figure 1 to pose a scientific question about an observation. Developing a hypothesis. How could you answer your question about cricket chirping? In trying to answer the question, you are developing a hypothesis. A hypothesis is a possible answer to a scientific question. You may suspect that the hot temperature affected the chirping. Your hypothesis would be that cricket chirping increases as a result of warmer air temperature. Use Figure 2 to practice developing a hypothesis. A hypothesis is not a fact. In science, a fact is an observation that has been confirmed repeatedly. For example, that a cricket rubs its forelegs together to make the chirping noise is a fact. A hypothesis, on the other hand, is one possible answer to a question. For example, perhaps the crickets only seemed to be chirping more that night because there were fewer other sounds than usual. In science, a hypothesis must be testable. Researchers must be able to carry out investigations and gather evidence that will either support or disprove the hypothesis. Disproven hypotheses are still useful because they can lead to further investigations. How do you design and conduct an experiment? After developing your hypothesis, you are ready to test it by designing an experiment. An experiment must follow sound scientific principles for its research to be valid. You know your experiment will involve counting cricket chirps at warm temperatures. But how will you know how often a cricket would chirp at low temperature? You cannot know unless you count other cricket chirps at low temperatures for comparison. Controlling variables. To test your hypothesis, you will observe crickets at different air temperatures. All other variables, or factors that can change in an experiment, must be the same. This includes variables such as food and hours of daylight. By keeping these variables the same, you will know that any difference in cricket chirping is due to temperature alone. The one variable that is purposely changed to test a hypothesis is the manipulated variable, or independent variable. The manipulated variable here is air temperature. The factor that may change in response to the manipulated variable is the responding variable, or dependent variable. The responding variable here is the number of cricket chirps. Setting up a controlled experiment. An experiment in which only one variable is manipulated at a time is called a controlled experiment. You decide to test the crickets at 3 different temperatures: 15 degrees Celsius, 20 degrees Celsius, and 25 degrees Celsius, as shown in Figure 3. All other variables are kept the same. Otherwise, your experiment would have more than one manipulated variable. Then there would be no way to tell which variable influenced your results. Experimental bias. In any experiment, there is risk of introducing bias. For example, if you expect crickets to chirp more at 25 degrees Celsius, you may run experiments at just that temperature, or, without meaning to, you might bias your results by selecting only the crickets that chirp the most often to test. Having a good sample size, or the number of crickets to be tested, is also important. Having too few crickets may bias your results because individual differences exist from cricket to cricket. Collecting and interpreting data. You are almost ready to begin your experiment. You decide to test 5 crickets, one at a time, at each temperature. You also decide to run multiple trials for each cricket. Before you begin your experiment, decide what observations you will make and what data you will collect. Data are the facts, figures, and other evidence gathered through qualitative and quantitative observations. To organize your data, you may want to make a data table. A data table provides you with an organized way to collect and record your observations. Decide what your table will look like. Then you can start to collect your data. After your data have been collected, they need to be interpreted. Probeware is one tool that will not only help you collect and record data, but can also help you interpret it by creating graphs. Graphs can reveal patterns or trends in data. Sometimes there is more than one interpretation for a set of data. For example, scientists all agree that global temperatures have gone up over the past 100 years. What they do not agree on is how much they are likely to go up over the next 100. Drawing conclusions. Now you can draw conclusions about your hypothesis. A conclusion is a summary of what you have learned from an experiment. To draw your conclusion, you must examine your data objectively to see if they support or do not support your hypothesis. You also must consider whether you collected enough data. You may decide that the data supports your hypothesis. You conclude that the frequency of cricket chirping increases with temperature. Now, repeat your experiment to see if you get the same results. A conclusion is unreliable if it comes from an experiment with results that cannot be repeated. Many trials are needed before a hypothesis can be accepted as true. Your data won't always support your hypothesis. When this happens, check your experiment for things that went wrong, or for improvements you can make. Then fix the problem and do the experiment again. If the experiment was done correctly the first time, your hypothesis was probably not correct. Propose a new hypothesis that you can test. Scientific inquiry usually doesn't end once an experiment is done. Often, one experiment leads to another. Communicating. Communicating is the sharing of ideas and results with others through writing and speaking. Scientists communicate by giving talks at scientific meetings, exchanging information on the internet, or publishing articles in scientific journals. When scientists share the results of their research, they describe their procedures so others can repeat their experiment. It is important for scientists to wait until an experiment has been repeated many times before accepting a result. Therefore, scientists must keep accurate records of their methods and results. This way, scientists know that the result is accurate. Before the results are published, other scientists review the experiment for sources of error, such as bias, data interpretation, and faulty conclusions. Sometimes a scientific inquiry can be part of a huge project in which many scientists are working together around the world. For example, the Human Genome Project involves scientists from 18 different countries. The scientist's goal was to create a map of the information in your cells that makes you who you are. On such a large project, scientists must share their ideas and results regularly. Come up with ideas for communicating the results of your cricket experiment in Figure 5. What are scientific theories and laws? Sometimes a large set of related observations can be counted. I'll just repeat this section here. What are scientific theories and laws? Sometimes a large set of related observations can be connected by a single explanation. This explanation can lead to the development of a scientific theory. In everyday life, a theory can be an unsupported guess. Everyday theories are not scientific theories. A scientific theory is a well-tested explanation for a wide range of observations and experimental results. For example, according to the atomic theory, all substances are composed of particles called atoms. Atomic theory helps to explain many observations, such as why iron nails rust. Scientists accept a theory only when it can explain the important observations. If the theory cannot explain new observations, then the theory is changed or thrown out. In this way, theories are constantly being developed, revised, or discarded as more information is collected. A scientific law is a statement that describes what scientists expect to happen every time under a particular set of conditions. Unlike a theory, a scientific law describes an observed pattern in nature without attempting to explain it. For example, the law of gravity states that all objects in the universe attract each other. Look at Figure 7. And that is the end of Chapter 1.